Hi, I'm Bill Cavness again, the director of the Asbestos Institute, and I wanted to go over a little bit of information with you, a general overview of the analysis issue. Analysis of bulk samples under the EPA regulation AHERA that really is applicable under most bulk sampling, even under OSHA. Okay, well, first of all, a quick word about the regulation itself, AHERA, that we get all of our regulatory applicability on bulk sampling, who can do it, how it's done, what happens to the samples, how they're analyzed, what the results of analysis means, and so forth. All of that is gone through by EPA. In this regulation, AHERA, if you have a copy, you might want to reference that and follow along with some of the things I'm going to talk about here. But I want to focus on bulk sampling and analysis, mainly the analysis end of that. A few general comments first. Under all of our regulations, EPA, OSHA, all of them, there is a basic method of analysis, a basic analytical method, and it's called PLM, or polarized light microscopy. And you understand that because this is a refresher class, not an initial training. But PLM, or polarized light microscopy, was designed in the early to middle 80s through EPA and Research Triangle Institute back east to give us a way to analyze, or to give a lab a way to analyze an asbestos sample, or a sample of suspect material like a sample of this wall system here, in a way that was inexpensive, that would give us as much information as possible on, is there asbestos present above a threshold amount, which is 1%, and if it is present, what type of asbestos is it? Is it chrysotile, amosite, chrysotolite, an amphibole, what? But it tells us how much is there. Now, mainly, we need to know this for the application of the regulations that have a threshold percentage. So the analysis is to give us the threshold percentage. Now, again, PLM is our basic method of analysis, but it's not the only analytical method that we have, and in fact, it may be the weakest of the analytical methods that we have. The other methods that we commonly use are TEM, transmission electron microscopy, and then variations of PLM and TEM like point counting and gravimetric reduction, and then analysis of residue by PLM or TEM. But anyway, the various methods I'll mention in just a moment. First, I want to get back to why analysis is done. If we look at, say, asbestos content in building materials, and that's what all of the regulations really are focused on. Do we have asbestos content? What is the percentage? Is it regulated? And so forth. If we start with the chart here, running from a level of 100% asbestos, if we could measure that, down to a level of 0% asbestos. So what we're looking at is asbestos content here. We need a method. If I cut a 1-inch square, say, piece out of this wall and take it to a laboratory, it needs to analyze the various layers in this sample in a way that I can tell what is the percentage if there is asbestos there. Now on this chart, we need a threshold here, 1%. I know this is not in scale, but that's our regulatory threshold. We need to be above that to be regulated. At that level and below, it's non-ACM. Okay, then there is another threshold right here, we'll say 10%. And that's the limit of accuracy of PLM visual estimation, our analytical method that this regulation, AHERA, gives us to use in the regulation itself as a minimum procedure. PLM visual estimation. Okay, now it's only accurate down to 10%. At 10% and above, it's pretty accurate, and it'll give us the information that's required. But it's not so important to building users or inspectors or contractors even to know whether they have 50% asbestos in the material or 70% asbestos in the material. What's important to those people, those regulated people, is am I above 1% or not? Because 1%, exactly 1% is non-ACM, non-regulated by EPA. And most regulations above that would be regulated. So that's the real question. Where are we in relation to the 1% thing? Okay, getting back to the analytical methods. We use PLM because it's fast and it's cheap, and it's the basic regulatory requirement under AHERA, okay? Below 10% though, by PLM, most experts would say is nothing better than guesswork. Even though we've had, 25 or 30 years even of analytical experience in this country using PLM, and we have some very good analysts, still, the method itself doesn't lend itself to be accurate enough with the most experienced analyst to be accurate below that level. So EPA recognizes that early on in this regulated industry, and they say, okay, below 10%, the safe thing to do is just assume positive, okay? So any level below 10%, this area right here, we assume positive. Assume ACM. Assume that it's greater than 1%, okay? Well, that's safe enough then to protect workers, to protect the public, and all that, building users. If we have the presence of asbestos, but we're not sure about the regulatory threshold here, we'll just assume positive. Okay, now below the 1% level, there are other levels, of course, clear down to 0, just like there are levels above that. So this is the idea, this is the regulation actually from EPA. Now, since asbestos work involves a lot of cost to building owners, and EPA wants to really be least burdensome, protect human health and the environment in the least burdensome way, we don't want to just saddle all the building owners in this country with millions upon millions of dollars in cost to deal with asbestos. Because what if it's really not asbestos? What if our analysis comes back in this area down here and we're not really sure what the number is because the method can't tell us? Then we need a way to prove that it's not ACM, so we don't spend these jillions of dollars in this country on asbestos controls with non-asbestos, okay? So what EPA did in the 1990 version of the NESHAP, our current applicable version of the asbestos NESHAP, was, and let me just say, that's really important because the NESHAP is the one regulation that requires that a building owner do asbestos removal work before demolition or renovation. It has the effect of doubling the cost of demolition or renovation to a building owner. That's the NESHAP. So the NESHAP says if you're below this level, this 10% level, you must point count a sample. Now, point count is a different analytical method using the same microscope, the PLM microscope. So the inadequacies, like for instance, the PLM scope can't see asbestos at this level. You can't see individual fibers at any level. I mean, you may have 30% asbestos in, say, a floor tile sample and get results by PLM back of non-detect, 0. But you have 30%. That's because the microscope can't detect, can't see the very small fibers that asbestos have. So anyway, EPA says below this level, you assume positive or point count. So to rebut this, or to prove that what you're working with is non-ACM, this is the area that we point count in. Now the point count is just a different way of giving us a result, a quantitative result, a real number result of analysis using the PLM microscope. Okay, so we're using the same tool in a little different way. We're counting differently. We count more spots instead of looking at a large picture, and it's called visual estimation. We get results like 2 to 5% ACM or asbestos. Okay, if we point count, instead of looking at the big picture, we count specific points randomly distributed across a slide with the optical piece in the microscope, and we report with a quantitative number. So we may get a number like 1.25% or 0.75%. Okay, but it's a real number. Now we can make an application to a threshold line like this. Okay, so to review very quickly, EPA requires assuming positive below this line analyzed by PLM. So we point count because we're down here in this area. We don't want to spend a ton of money on this if it's not really asbestos. We do the point count, we get down here to real numbers instead of a range, and we simply apply those. So this one would be above the 1% line and would be ACM. This one would be below the 1% line, would be non-ACM. And EPA would walk away, would not regulate them. Okay, well that helps a lot in bringing the focus more clearly into perspective on where we are in relation to that 1% line. But with this microscope and this analytical procedure, it's still pretty fuzzy. I mean, that whole area inside that oval that I drew right there may or may not be asbestos. It doesn't matter what the microscope says. It may or may not be greater than 1% asbestos. And it's foolish to represent a building owner and say it doesn't matter, because all of us have seen major asbestos jobs that cost the building owner millions of dollars on an individual project. So it's really important that we know, do we have to spend those millions or not? All right, so EPA takes one more step to try to clarify even this point count number, which is a big step. And they go to another little scale here. And this scale is 2% and 1%. Okay, where 2% is ACM, greater than 1% asbestos, 1% is non-ACM. Okay, in between here, there is 1.5. So once we get this quantitative number by point count or any other method of giving us a quantitative result, an accurate quantitative result, then we take these numbers and apply them to this little scale. And if we're below 1.5, and both of these would be, see, then we round down to 1%, which is non-ACM. If we're at 1.5 or 1.50 by point count or other analytical method that gives us this quantitative number, we round up to 2%, which is ACM. This is not some kind of a foolish rule that people should ignore, and I've heard that comment made by good industrial hygienists, good consultants in our industry, but this rule was written into the regulation that we call a HERA as an appendix. It's Appendix E to what we call a HERA, and it is the analytical method. And this step was taken in this analytical procedure to try to get to a more accurate number to define where we are in relation to that 1% line. And it's really important because, like I said, tons of money are spent on that. Okay. Quick word about other methods of getting to that quantitative number. We can get there by point count. See, we can't get there by straight PLM visual estimation. That gives us this range, whatever the range is. We can get there, though, by quantitative analysis. Another quantitative method that is no doubt the most accurate way we have to analyze any suspect material for asbestos is called gravimetric reduction and analysis by TEM, by transmission electron microscopy. Okay, the reduction, gravimetric reduction, meaning we're going to weigh this sample to start with. We know exactly what it weighs in the laboratory, and then we reduce it through several steps, several regulatory steps. One would be to ash it or burn it or cook it at a very high temperature and end up with a pile of ash instead of a sample like this. So we ash it and then weigh the ash. So we know where we were weight-wise to start with, what we have left once it's ashed, and then essentially we just dissolve that ash residue in a hot acid, and some of it will dissolve away and some may not. Now whatever is left we weigh again, and it's more complicated than this simple explanation, but essentially that's it. We end up with residue that is not affected by high heat or acid, and we analyze that. Now, if we analyze that residue by TEM, then we have the most accurate analysis of whether we have greater than 1% or not in our material that we're analyzing. Or we could analyze the residue by PLM, which should be very accurate if we've taken away any masking, any matrix masking, so that the PLM can at least see fiber bundles. But TEM would be the most accurate. Okay, now that method, gravimetric reduction and analysis by TEM, takes longer and costs more money. For a single sample, that may not be a big deal to a building owner. You may be talking about the difference between $10 and $50. But across the United States, asbestos jobs, asbestos control, where we may be looking at millions of samples analyzed at different laboratories, we're talking about an awful lot of money, an awful lot of resource taken out of circulation and given to this project. So it is expensive and it takes more time. However, it costs, the cost is negligible compared to the cost of removing asbestos before demolition or renovation.